So now let's talk about the second one, right? So pay attention that in the case of the encoder, in the case of the decoder, I cannot use the future input, right? So it's a causal system. In the case of the decoder, I'm sorry, in the case of the decoder, I cannot use the future words. In the case of the encoder, right? So we actually can condition on the future and gets a bidirectional context, okay? And BERT is one example, and you know, we don't know exactly how to train that model yet, right? Because apparently the language model is probability of xt given x1 to xt minus 1, right? So that's not exactly what applies here. Look at this major differences, right? Shown in the, you know, pictures, right? Okay, now let's look at these, you know, encoders, right? That are bidirectional. So in other words, you know, it has the context from the words ahead of this current word and the words after the current words, which makes a lot of sense actually, because you know that, you know, this direction and the grammars are different in different languages. Sometimes we put the verb somewhere in between the subject and the object, but in some language, for instance, the verb is at the end, right? So you really cannot assume that the context in the natural language is coming only from, you know, the past or, you know, the words ahead of it, right? But that's what we had to do for the, you know, for the decoders, right? In the encoders, we can actually use both directions, but that also means that we cannot do language modeling anymore, okay? So what do we do instead? So the idea is the following, right? So I still have this sentence, right? So I went to the store, for instance, but as an input, I will mask some words, meaning that I will replace that word by a special token called a mask, okay? And my pre-training task, or the output, would be reconstructing these masked tokens, okay? So this is also called a masked language modeling, okay? Be careful, this is not exactly the same as the masked self-attention, okay? Be careful about that. Don't get confused, okay? This is a masked language modeling. So in other words, you are learning P of x sub t given, right? Let's say this is x sub t, given x sub minus t, right? X sub minus t means all the words except xt, right? Right? So that's a different distribution that we are learning, right? This is a masked language models. But there are a lot of details that are much more complicated than just doing that, okay? So BERT, this 2018 paper, right? So what they do about this masked language model for BERT is the following, okay? So they will randomly choose 15% of the word tokens, right? But you don't just always replace those chosen words by a mask token. Why? Well, if you always, you know, replace those words by a mask token, then language models pretty much are already, you know, fixed on the idea that, oh, whenever you are asking me to learn these embeddings, this must be an embedding of a masked word. I never have to worry about the words that are not masked, right? So instead, you want to actually introduce some uncertainty and let the language model learn a little bit more. So you do replace the input word with mask, the special token, but only 80% of the time, okay? And then, you know, but for other 10% of the time, you will replace this input word by a random token that's not a mask, a random word. And for the last 10%, you don't change it, but still, okay, right? Still, the transformer has to predict the word, but this time it doesn't know exactly whether it was masked or substituted or unchanged, right? Right? It has to learn something from that, right? So, so that's what I'm saying here, that you don't want the model get complacent and not build strong representations of non-masked words, okay? In other words, this is what I was saying about why you want to introduce this uncertainty. 3 kind of scenarios, right? Now, after all, in the fine-tuning time, we don't have masks, right? So this is only used, a token specially introduced for the pre-training stage, right? This is another instantiation of the idea of constructing your pre-training data and task in a way to conform to your model architecture, right? Or the fine-tuning tasks as well, right? So BERT. BERT is a bidirectional encoder representation from transformers, right? So you sort of have a very small differences between the pre-training and the fine-tuning stage, architecture-wise. So that's what we want, right? We want to pre-train the model parameters as much as possible, right? So you have to change idea of borrowing part of the architecture and use different tasks. Instead, you want to do repositioning your pre-training tasks so that you can utilize the same architecture as much as possible, right? So it's very simple. That you see, it's very similar architecture. In the pre-training stage, you have this masked language modeling, right? And in the fine-tuning stage, you actually have very much the same architecture. But this could be a different task. This could be a task like the question asking, right? This could be a question asking and answering, excuse me. And then your data in the fine-tuning stage, right? In the pre-training stage, of course, just the unlabeled sequence A and B pairs, right? And in the fine-tuning stage, you have the question-answer pair, right? Notice that how you are, not only right? So that you can utilize the architecture similarity between the 2 stages, you also have to make sure that the data are fed into the architecture in the similar way between the pre-training and the fine-tuning, right? So this is in the fine-tuning, you have the question and the paragraph, and then there's a separation like the delimiter we introduced before, right? And this is how you pre-train BERT, okay? Any questions so far? And this could be pre-trained for different kind of downstream tasks. These different names are different downstream tasks, okay? Any questions so far? Okay, so again, this is something like what I said before, a little bit more details about pre-training BERT, right? So again, as we said before, you have a pair of sentences, right? So you have a pair of sentences, right? Start with starting token, sentence 1, and then separation, and sentence 2, right? That's the input, right? So pay attention that your token embedding and the segment embedding and the positional embedding, okay? And then BERT was, the way you construct the sentence 2 is kind of tricky, right? So the sentence 2 actually could be, real in the sense that it follows sentence 1. But it could also be like a, junk that is not really following sentence 1, okay? Then the BERT will be pre-trained to predict whether text 2 or sentence 2 is randomly sampled or it's really following sentence 1, okay? So this is something similar to what we introduced earlier on, but this is very interesting. So this is some dubbed as the next sentence prediction, okay? But later work has argued that this kind of next sentence prediction may not be necessary. So a little bit more details about the BERT. I think these models are getting bigger and bigger. We are talking about the number of layers, the number of attention heads, right? This is multi-head attention. And this is a dimension of the hidden state, right? And you can train such models on very large data, right? Books corpus or English Wikipedia. That's the benefit. We're saying that there are so many unlabeled data. But the tricky part is how do you design pre-training tasks, right? Lately in NLP, there's a new kind of ways called prompting is being introduced, right? So, but you can think of it right now as if it's a more general kind of pre-training. And these pre-training are often on large models and huge data, and then they usually have to be pre-trained using a lot of resources, right? But the good thing is that many of these pre-trained models are already pre-trained by others, and they are released through very friendly interfaces, right? Do you know Hugging Face, for instance? Right, there are a lot of models, including protein sequence models, deposited through the Hugging Face interface. And you can actually use that model, pre-trained model, and fine-tune it with much smaller data set with much less resources, including GPUs, DPUs, or time, right? So that's, and you can do that many times for different tasks. So this is a benefit of pre-training fine-tuning, okay? And well, we talked about the second one, that is pre-training the encoders, right? So they look great, and do you worry about anything, right? So do you worry about anything? Well, you actually have to think about it, right? So if, we talked about the pre-training the encoders, right? So, but, and in the case of the decoders, right? In the case of the decoders, right? So if you are interested in generating sequences, like designing the protein sequence, right? Then you probably want to consider a pre-trained decoder, right? Right? This is only depending on the past, right? And then, as I said, you can use the autoregressive way of sampling and generating the whole sequence, right? One by one, right? And then, if you consider BERT or other kind of pre-trained encoders, they don't really lead to this kind of nice sequence generation performance, okay? Then this sequence generation is in the autoregressive way, like one word at a time, as I said. You feed, start, and you get the first word, and then put the first word into this second input, and you get the second word, and so on, right? So this is called autoregressive generation. Any questions so far? Okay, so BERT has been extended, right? A lot of variants, and one of them is Roberta, and one of them is Span-Robert. So a quick summary of the differences, right? So Roberta is basically BERT trained longer on larger data, and then the next sentence prediction I introduced about, to predict the next sentence is random or not, is removed. Okay, that's their argument. This is not necessary, right? And the Span-BERT is when you're introducing the masks, right? They actually put a mask on contiguous spans of words, right? So this actually makes a harder and more useful pre-training task. This is actually utilized in protein sequence modeling as well. If you remember RGN, which was using the recurrent neural network to predict the protein structures from the input sequence. And I asked you last time that they have RGN version 2. Do you want to guess what's the model architecture? And you guessed correctly that the model architecture is transformers, right? But they actually also use the idea of Span-BERT, that when they are masking residues, in our case characters or residues, they actually also consider the contiguous k-mers, right? We know that the importance of the contiguous k-mers, right? So that's what they do as well. And this is what Roberta paper is taking away, right? So basically, they take longer time, right, to pre-train, and then use more data, right? And then even if you don't change the underlying transformer encoder, your performance can get better, right? So that's what their take-home message. Okay, lastly, how you can pre-train encoder-decoder together when your architecture is, like this, right? And the example, including the visual, the image captioning example I told you before, and then one example is called T5, for instance. So how do we pre-train encoders and decoders together? What pre-training objective to use? Remember, this is something like optimization. You have to provide the data. You have to introduce a task that can be translated into a loss or objective function, right? So what objective function or loss function to use? We could do something. So again, pay attention that which one is encoder and which one is decoder. Blue one is decoder. How did you tell? I thought the red one is sparser. So across the two is the cross attention, okay? But you're right that the sparser connectivity tells the decoder, and more specifically, it's sparser in the way that it only depends on the current and the past, but never the future. All right? So this is what so encoder and decoder. Encoder is bidirectional, okay? And decoder is sort of causal. And then in between, there's a cross attention, okay? All right, so there's a cross attention and self-attention, right? This is the masked self-attention, which is causal, does not depend on the future, and this is just the self-attention, bidirectional. Okay. We could do something like the language modeling, but you have to wonder, where a prefix of every input is provided to the encoder and is not predicted. Okay, let's look at this expression again. We have the H, right? We have the W fed into the encoder, and we get the H, and then H fed to the decoder together with this W, right? And we get the the HT plus 1 to H2. And then in the end, we feed them to these linear layers, right? So the encoder portion benefits from the bidirectional context, and the decoder portion is used to train the whole model through the language modeling, right? So that's something we can do. So for instance, specifically, what do we do, right? So in one paper, right? So one way to do this is called the span corruption. It's very interesting, and T5 is using this kind of pre-training, right? So they have the encoder and the decoder. So this is what they do, okay? So they replace the different length spans from the input, like the span. Let's see, span BERT, span BERT, yes, like the span BERT to some extent. And so we don't know the length of these, these things that are going to be placed under almost like a mask. And then we try to use, so where the input is going to give this sentence, and some things are masked out. We don't know the length. And the output of the decoder is going to have to guess what's out there, right? So in this way, you can see that in the encoder part, right? So it's this encoder part, I still can have the bidirectional thing, but the decoder part, I'm doing the language modeling. It's very similar like the language modeling from the decoder side, okay? So this is what they introduced called span corruption. But notice that they don't, they corrupt, they mask out entirely. But they don't do this random substitution or random preservation anymore. That's different from what you have seen before. And they found that this encoder-decoder, right, work better than decoder for their tasks, right? And then the span corruption, work better than language modeling for the pre-training. Okay. Any questions so far? So far, yeah, this is an example about T5, for instance. Okay, the T5 is it can be fine-tuned to answer